On Christmas Eve 2024, NASA sent a spacecraft directly into the atmosphere of the Sun. Then it disappeared. Mission Control lost contact completely. For 2 days, nobody knew whether Parker Solar Probe had survived.
The Parker Solar Probe just made its closest approach to the Sun.
On December 26th, the signal finally came back. And almost immediately, scientists realized something uncomfortable. Because what Parker Solar Probe measured near the Sun did not behave the way a star is supposed to behave. The temperature increased in the wrong direction. Magnetic fields folded back on themselves, and streams of solar material appeared to reverse course mid-flight. And the deeper scientists looked into the data, the less the Sun started making sense. For decades, physicists believed they broadly understood how stars like the Sun behave. Not perfectly, but well enough. Heat should move outward from the hottest regions. Energy should gradually disperse. The outer atmosphere should cool as you move farther from the surface. But the Sun does the opposite. Its visible surface sits at around 10,000 degrees Fahrenheit. The corona above it can exceed 2 million, and nobody has ever fully explained why. That contradiction has existed at the center of solar physics for generations. Not as a fringe idea, as a measured reality. You can feel how wrong it sounds immediately. If you step away from a fire, you expect less heat, not more. But above the Sun, the temperature climbs violently upward. And Parker Solar Probe was built to fly directly into the region where that contradiction begins. The spacecraft launched in 2018 from Cape Canaveral aboard a Delta IV Heavy rocket. Its mission sounded almost impossible from the start. Fly closer to the Sun than any spacecraft in human history and survive long enough to measure what is happening there. The probe was named after Eugene Parker, the astrophysicist who proposed in the 1950s that the Sun constantly releases a stream of charged particles flowing across the solar system. At the time, many scientists rejected the idea completely. A star producing a permanent solar wind sounded unrealistic, but later missions confirmed it. Parker had been right. The problem was that his discovery created another mystery. If the Sun continuously ejects material into space, what accelerates it? What heats it? And why does the corona behave like a region where energy is somehow being added instead of lost? To answer that, NASA and engineers at Johns Hopkins Applied Physics Laboratory had to build one of the strangest spacecraft ever designed. Not a spacecraft that avoids heat, a spacecraft that survives inside it. Parker Solar Probe carries a carbon composite heat shield nearly 5 inches thick. The shield absorbs temperatures approaching 2,500 degrees Fahrenheit, while the instruments behind it remain close to room temperature. But heat near the Sun behaves differently than most people imagine. Space itself is mostly vacuum. Without dense matter, heat transfer changes completely. Survival depended less on distance alone and more on perfect alignment. If the spacecraft tilted too far away from the Sun for even a short moment, direct radiation could strike the instruments behind the shield. There would be no dramatic explosion. The spacecraft would simply stop existing as a functioning machine. And by late 2024, after repeated gravity assists around Venus, Parker entered the closest approach ever attempted. At perihelion, the spacecraft came within roughly 3.8 million miles of the Sun's surface, closer than any object humanity has ever sent. Its velocity reached around 430,000 miles per hour, fast enough to travel from New York to Los Angeles in under 30 seconds. Then communications stopped. No steering corrections, no live updates, no direct human control. Just silence. Inside Mission Control, engineers waited while Parker disappeared behind the Sun and entered the corona alone. And this is where the story becomes less about engineering and more about instability inside reality itself. Because once Parker began transmitting data again, scientists saw behavior they still struggle to fully explain. The spacecraft repeatedly encountered sudden magnetic reversals called switchbacks. Imagine a river violently turning backward before snapping forward again. That is essentially what Parker measured in the solar wind. Magnetic fields folded sharply back on themselves. Plasma streams appeared to reverse direction. The structure of the corona looked far more chaotic than expected. Researchers initially believed switchbacks might finally explain the heating problem. The explanation seemed almost convincing. Magnetic fields store enormous energy. If those magnetic structures suddenly reconnect or collapse, they can release energy directly into surrounding plasma. That energy could heat the corona. But the deeper scientists analyzed the measurements, the less complete that explanation became. Switchbacks explained part of the behavior, not all of it. And this keeps happening around the Sun. Every new answer seemed to expose another unstable layer underneath it. ESA's Solar Orbiter mission has been observing the Sun from farther away, while Parker flies directly through the solar material itself. One mission observes the structure, the other enters it. Together, they are building a picture of a star that behaves less like a stable burning sphere and more like a constantly shifting magnetic system. And the consequences reach directly to Earth. The solar wind is not just a scientific curiosity. It carries solar storms across the solar system. When powerful eruptions strike Earth's magnetic field, they can interfere with satellites, disrupt GPS systems, damage communications infrastructure, and in extreme situations overload power grids. The famous Carrington event of 1859 generated electrical surges powerful enough to ignite telegraph systems. A similar event today would hit a civilization that depends on satellites, navigation systems, and global electrical infrastructure every second of the day. Which means this mystery does not stay near the Sun. It reaches here. And that is what makes Parker Solar Probe feel so unsettling. Humanity touched a star, not metaphorically, physically. We sent a machine directly into the atmosphere of the object that makes life on Earth possible. And instead of making the Sun feel simpler, the mission exposed how unstable our understanding of it still is. There are serious explanations being tested right now. Magnetic waves moving upward through the corona. Tiny reconnection explosions occurring continuously across the solar atmosphere. Turbulence transferring energy between magnetic structures and plasma. All of them explain part of the picture. None of them fully close the problem. And maybe that is the deeper reality Parker is forcing scientists to confront. The Sun may not operate through one clean mechanism hiding beneath the surface. It may be multiple violent processes interacting simultaneously inside a magnetic system far more dynamic than we originally believed. Which means the mission did not simply bring humanity closer to the Sun. It brought us closer to a region of reality where some of our most basic physical expectations stop behaving normally. And somewhere inside that brightness, the part that should cool down still keeps getting hotter.